This year, there were two major experimental results that could change physics forever, and both were related to muons. But what are muons? Before defining them, let's take a look at the way particles behave in a magnetic field. When a charged particle is shot into a uniform magnetic field, it will describe a curved trajectory, and every type of particle describes a different trajectory depending on their charge-mass relation. In 1936, researchers were investigating the way that electrons move in a magnetic field when they saw a particle with a much wider arc. That particle was the muon, and it had very similar characteristics to the electron, but it was 207 times heavier and more unstable. Physicists don't really know the reason behind this property, and they suspect it might actually break in a specific case. Having understood that, let's take a look at the experiments that made the news. First, we have Muon G-2 at Fermilab. This experiment used a big circular magnet to measure the gyromagnetic factor, or G factor. And what is the G factor? Well, let's make an analogy. Have you ever seen a spinning top? You might have noticed that it doesn't just spin along its axis, but it also wobbles. That wobble is caused by the gravitational field, and it's called precession. In the same way, in the presence of a magnetic field, the muon will wobble. So, what the G factor measures is the amount of wobble of the muon. If muons were solid objects, like spinning tops, that G factor would be 2, but that's not the case. Muons are decaying and recombining all the time, and sometimes doing both at the same time. That phenomenon, which we'll call quantum foam, affects the wobble of the muon. So to really know the G factor, we have to add a correction value for the effects of the quantum foam. Finally, the calculated value was this one, and the number they found was this one. Now, you might think that's a small difference, but with the amount of precision of this kind of experiments and calculations, that difference is very significant. Moving on to the LHCb. This experiment is testing the limits of leptonic universality, and by doing so, also searching for weak points in a standard model. How are they doing that? Do you remember that I told you that there might be a case in which this property breaks? Well, scientists have long suspected it happens in the decay of the B meson, which can result in a combination of particles that include either muons or electrons. According to the leptonic universality, the amount of electrons and muons produced in the decay should be roughly the same. But what they found is that for each electron, only 0.846 muons were detected. And now, what do these results mean? What might be causing them? Is it a force we haven't discovered? Perhaps a particle? We honestly don't know. The results are exciting because they might challenge what we know, but they might just as well be statistical anomalies. If it's one or the other, we should be happy, because it's all part of the process of understanding our universe. Thanks for watching.